There is an assumption that to scale an AI system, you need to build complex, state-accumulating reasoning engines that operate with near-total autonomy. When you let these systems run unbounded, they inevitably fall victim to context drift, cascading coordination failures, and logic deadlocks that usually only surface after deployment. But a comprehensive 2025 empirical study surveyed over 300 practitioners running real AI agents in enterprise production and found something entirely different. The data shows that the most successful deployed systems are rigorously bounded and highly constrained. Rather than utilizing open-ended reasoning loops, they rely on strict step limits and mandatory human-in-the-loop checkpoints. To scale reliably, the industry is abandoning monolithic frameworks in favor of stateless handoffs and strict protocol boundaries. Achieving true agentic scale doesn't come from granting unlimited freedom. It requires designing systems with deliberate, hard-coded restrictions. The primary bottleneck in multi-agent systems is step count. As the number of autonomous steps increases, non-determinism compounds and reliability drops sharply. This chart maps the reality of production deployments. 68% of production agents execute a maximum of 10 steps before requiring human intervention. Zooming in further, nearly half of all systems restrict their execution to fewer than 5 steps. Keeping execution traces this short prevents minor logic errors from snowballing into hallucinations and cascading failures. Looking at model preferences, 70% of production systems rely on prompting off-the-shelf proprietary models instead of fine-tuning open weights. These off-the-shelf models provide predictable, established reasoning baselines that are easier to control. And to maintain that control, developers overwhelmingly favor manual prompt construction over automated prompt optimizers in high-stakes environments. These constraints are born out of necessity. These systems span highly regulated domains, like global finance and banking, major tech infrastructure, and large enterprise operations, where a single failure is incredibly costly. Because generalized automated benchmarks cannot test bespoke company workflows, these domains rely almost entirely on human-in-the-loop evaluation pipelines. High-impact deployment is an exercise in strict workflow restriction. Practical AI value comes from tight control, not open-ended reasoning. If reliability strictly requires short execution traces, we face a structural dilemma. How do you process a massive, complex enterprise workflow? You shatter the monolithic workflow into a network of highly specialized, single-purpose agents. OpenAI's Swarm is an architectural framework explicitly optimized for this type of lightweight, controllable coordination. Unlike stateful tools such as the Assistance API, Swarm focuses entirely on execution rather than memory management. It deconstructs orchestration down to 2 core primitives: agents, which encapsulate specific instructions and tools, and handoffs. The client run loop is simple: get a completion, execute tools, switch the agent if necessary, and return. Swarm is entirely stateless between calls, powered by the Chat Completions API. No hidden state machine accumulates data, preventing context drift. When an agent needs to transfer control, it executes a handoff by simply returning a new agent object as a function result. Context variables travel explicitly during this handoff. Developers have absolute, granular control over exactly what data moves forward to the next agent. If an error occurs, the system appends the failure directly to the chat history, allowing the isolated agent to recover gracefully without crashing the entire network. By making control transfers explicit and entirely stateless, developers eliminate the opaque orchestration layers that typically cause multi-agent systems to collapse. Internal framework logic is only part of the equation. Enterprise systems must interact with external databases, APIs, and agents built by completely different vendors. Relying on custom, hard-coded API integrations creates brittle systems and immediately breaks observability at scale. The 2026 AI Agent Protocol ecosystem defines strict architectural boundaries. The foundation is the tool access layer, governed by MCP. MCP standardizes agent-to-tool communication to expose data endpoints, but MCP is built solely for passive capability providers, like databases, not active peer coordination. For active orchestration, the stack moves up to the agent coordination layer, using the agent-to-agent, or A2A, protocol. A2A is required when delegating subtasks to autonomous peer agents. For example, a sales agent needing to coordinate with a pricing agent. The core mechanism of A2A is the agent card, a metadata file outlining exact capabilities and inputs. It enables dynamic discovery without hardcoding while enforcing strict OAuth authentication. Unlike Swarm, A2A maintains stateful task lifecycles across different vendor systems to prevent black box failures. Strictly separating passive tool access under MCP from active peer delegation under A2A prevents the monolithic architectures that inevitably fail under enterprise scale. Ultimately, a reliable multi-agent system is not an unbounded digital brain. It is a highly rigid composition of specific constraints. In a complete decoupled pipeline, a high-level orchestrator uses A2A agent cards to securely delegate a specific bounded task to a subagent. That delegated task executes within a stateless swarm agent, adhering strictly to a loop of fewer than 10 steps. During that loop, the agent securely pulls data through the MCP layer without breaking its internal stateless execution. And for the final action, the agent executes a strict, explicit handoff to a human-in-the-loop validation gate for final approval. This decoupled pipeline prevents context drift, bounds reasoning errors, and ensures seamless vendor interoperability. The future of enterprise AI does not involve giving agents limitless autonomy. It requires defining the precise protocols, boundaries, and stateless handoffs that make their autonomy safe to deploy.